Alrighty, good morning, lads and ladies. Welcome back to College Algebra. I want to talk to you about a couple kind of bookkeeping things today before we get moving. So without further ado, I'm going to turn on my screen share here. Let's get over to QCam. Started. Okay, so zero things, zero. So I'll put that shadow. Say the 18th now? Yeah, 18th, right? Alrighty. So I've received a few questions about grade books and stuff. I wanted to clarify there. The grades for this class, we talked about this early on, but it's been a while and I think a few people just had time to forget. The grade book for this class are all in my math lab. I've tried to turn the Canvas gradebook all the way off. I don't know if that was effective or not. I think it's one of those features in Canvas that you can't like disable because it's sort of inherent to the system. But we don't use the Canvas gradebook in this class. If you want to see how you're doing in the class, like what your grade is right now, the thing you need to do is check the MML gradebook. Your grade in my math lab is your grade in the class. The only things that go into the Canvas gradebook are the test scores because the tests are done in Canvas, but everything else, the homework, the quizzes, the activities, the projects, all of that is actually graded in MML. And then a little announcement. I guess this is kind of two parts. So first, I've added the 3% bonus from the exam one reflection. So if you did the exam one reflection, then your exam score in MML has gone up by 3%. And I didn't go in and decide who did a sufficiently deep exam one reflection. If you completed it, you got the 3%. So everybody who did the exam one reflection, congrats, you've added 3% to your exam one score. And for a lot of people, that brought us from D's to C's or C's to B's, some B to A's. So I'm really glad that you guys did that. The vast majority of people did, and I think that's awesome. Beyond giving you some extra points, I hope that you take to heart the sort of questions that asked you to think about. And I really, truly am curious to hear from you how helpful you think it was. Was it helpful? Was it totally useless? Did it mean anything to you? If so, let me know. If not, let me know that too. If it was just stupid and you hated it and you never want to do it again, you can say that also. The second thing here is that I got permission. So we will do an exam two reflection. And the same rules apply. So some people have been asking about this, and I said, well, I'll talk to my department chair, and if I get permission from them, as long as it doesn't mess up the digital learning plan DLP thing that they're trying to do with these exam reflections, I'd be happy to do another one. And again, offer the 3% bonus for anybody who completes it. So be on the lookout in Canvas. I have to get them to send me the thing because it's a part of the DLP. I can't just like create it myself. That's tied into the big math canvas here at Santa Fe because they like to track those things for statistical purposes. But there will be another exam reflection showing up in Canvas, just like the exam one reflection, same questions, same sort of thing. And if you go in there and complete the exam two reflection, I will add 3% bonus to your exam two score. So there's that as well. One more thing. A surprising number of people either missed exam two or didn't submit work. Submit. These people need to contact me. To avoid a 0. Right. The idea of giving a 0 for a test is something I really hate. I just want to see what you guys know. And frankly, it doesn't matter too much to me when. I just need to see that you've learned the material. I need to see in a proctored environment that you can solve these problems. And if you can show me that, then I am happy to give you a grade for it. So if you missed exam 2, please reach out. I think I had like 4 or 5 people who missed exam 2 altogether, and another 2 or 3 people who didn't submit their written work. Depending on the circumstances, if the written work is somewhere with a timestamp that I can trust, then you can get me that written work. Like if you took a picture and it's up in iCloud and iCloud has a timestamp on there that I can trust as being legitimate, then I'm happy to take that work and grade it. If you missed the test, then you need to reach out to me so we can figure something out. I don't want you to get a 0. Even though we're well outside the syllabus guidelines for a makeup test, I would rather work something out with you than just give you a 0. So if you missed the test, please talk to me. And if you didn't submit your written work for the test, again, please talk to me because I hate the idea of giving you a 0. Folks who didn't submit their written work aren't actually at risk of getting a 0 for the whole test, but they are at risk of getting a 0 for all the free response questions, which is 60% of the tests. So I would hate to see that happen. But that's it. Those are all the announcement-y things. Any kind of questions about this stuff for me before we get into the actual math for today? Okay. So last time we left off talking about operations on functions. So today, we're going to talk a little bit more about operations on functions or operations with functions. And we're going to talk about one-to-one functions. And their inverses. So in particular, when it comes to operations on functions, the only thing that I wanted to talk about that we didn't get to talk about on Tuesday, this first subject, which is homework 14, right? The only thing from homework 14 that I haven't been able to show you just yet that I wanted to show you is a really cool kind of diagram to help you understand what that fog thing is, the composite function. And understanding what I'm about to show you will help you understand inverse functions, I think. These are called machine diagrams. And this might seem kind of trivial at first. It might be like, oh, well, duh, you know, I don't see the value of this. But the metaphor is pretty useful, especially when it comes to discussing things like composites and one-to-ones. So remember the notation that we use for a function. I might call the function f, right? So here's what I do. I kind of pretend like f is a machine on an assembly line. And it's the F machine, right? It does F to things. You can insert whatever vulgar joke you want to help you remember that. But what the F machine does, it has an input spot over here, and it has an output spot over here. And what comes into the F machine are its inputs. And we usually think of the inputs as being X's, right? So here's our F machine. It's sitting on the function assembly line, and it takes in the input x's. And then what does a function do? Well, it takes in an input, it does something to it, it hits it with a hammer or it pulls its pants down or it squares the input, it does something like that, right? It does something to the input and it spits out an output. And the output we call f of x. So like f of 2 is the output you get when you feed the f machine the input 2. F of pi is the output you get when you feed the f machine the input pi. And f of x is the output you get when you feed the f machine the input x. So this over here is like our output. This is called a machine diagram. And on its own, it's not super exciting. Just talking about one function at a time, I think it might help us to have some sort of intuition about what functions are. Every input leads to a unique output. But the big idea here is that you can chain these things together, right? You can imagine like on a soda bottling line, right? Maybe an empty bottle comes in and a full bottle comes out, right? So the F machine is the machine that fills up the soda bottle. That would be a function. The output of that machine is a function of the input. Something else that might happen if you were inside of a soda factory, after the bottle gets filled, so it comes in empty, it gets filled, it comes out here, there might be another machine over here that like puts a label on the soda bottle. So let me describe a little bit what I'm talking about in more concrete mathematical terms. Again, this would be the machine diagram for the function f. These get interesting when we talk about machine diagrams. For a composite function. So let me take my little F machine. It takes in the input x and it spits out the output f of x. And imagine I have another function over here. This would be, I'll call it the G machine. And the G machine does the same sort of thing that the F machine does. It's going to take in an input and spit out an output. But the big idea with composite functions is that I connect the one machine to the other. So now the output from the F machine is the input to the G machine. And the G machine, again, does the same thing that the F machine does. It takes in whatever you feed it, and it spits out G of that thing. So out of here would come G of F of X. That's the output from the G machine when I stitch its input up into the output from the F machine. So this is what the G machine is going to be spitting out now. You can think of it, I think a metaphor I used when I taught this in person was on the human centipede. Again, nasty, but it works. This is like the human centipede of functions. Yeah, you stitch the output from one machine up to the input from another machine. If you haven't seen the movie, ignore the joke. These two things together, when you connect them like this whole thing. So if you want to think of this as a single machine, all right, so inputs go in here, outputs come out here. This whole thing together would be a composite machine. This would be the machine for G of F. Because look at what comes in. X's come in. Look at what comes out. G of F of X. And if you swap the order of the F and the G machines inside, so you have a G first, and then you attach to the G machine on the output side the F machine, I should have made that bigger. So if you link these guys together, X's come in, out from the G machine go G of X's. You feed that into the F machine, then what will come out of this is F of G of X. So you ready for the really bad joke? This is the fog machine. All right, this is the machine diagram for the composite function F of G of X. And it turns out this is a really useful way to think about functions. Right. It's a little bit counterintuitive. One of the reasons I like this is because it explains sort of why these things show up in the order that they do, or kind of explains the counterintuitive nature of this notation. So when we read F of G, right? F circle G like this, the composite, F circ G, we usually think of F as coming first and then G. And when you write it down like this, it does look that way, right? It's F of G of X. And that's precisely why we have this notation. But when you ask what it's really doing, it kind of does the G function first and then does the F function. So when you look at, for example, G of F of X, this thing, and you ask what order are the functions being applied, really it's F of X that happens first, and then we're taking G of that. This is G of F of X. So if you want to figure out what is G of F of 2, remember what we talked about the other day. I said start on the inside. You have to start on the inside and work your way out. This is why. And I hope that these machine diagrams help a little bit understanding why we work from the inside out. It's precisely this assembly line logic. Okay. I wouldn't mind looking at one more problem, just one more from the homework there. What is it, homework 13? Homework 14, operations with functions, before we get into the next round of content. And I believe I had it. Oh, no, it's posted. All right. So we can take a look at one more problem from here, and then we're going to go on to the homework 15 stuff, which is about inverses. Very, very cool. So we got the opportunity to do some of these earlier. I think it's best that we look at one of these with the tables, because these sort of things are precisely what's useful here, the machine diagram stuff. So let's do that. All right. So rather than copying down the table, I don't want to burn the time on that. Let me just take a look and I'll solve one part of this problem, one or two parts of this problem. So we're given these two tables. There's a table for f of x. So here's some x's, and here f of those x's. So like f of 3 is 6, f of 6 is 3. Here's a table for g. G of 1 is 3, g of 3 is 4, and so on. We're asked to find f of g, g of f of 3. So This is, what number was this? Just for reference purposes. This is homework 14, number 18. We're going to use the table. I use the tables to find G of F of 3 and F of G of 4. Water. So somebody remind me, we talked a lot about this on Tuesday. What's the first step to doing this? What do I need to do first in order to find G of F of 3? What should be our very, very first step? And we're thinking just about mechanics. Right, very good. We need to start by just writing out the rule, write out the definition. What the hell is this notation? What does it mean? Well, this is just a fancy way of saying I want G of F of 3. And then remember our machine diagrams. Remember what we were just talking about, right? If I want G of F of something, the G of F machine, I need to figure out what F does first, then figure out what G does to that. In other words, we work from the inside out. I need to figure out what F of 3 is, then I can figure out what G of that is. So, looking at my table, what is F of 3? Excellent, Kendra. Yeah, this is 6. Gabe, thank you too. So if we look at the table here for F of X, we go to the X row where there's a 3. When X is 3, we see F of X is 6. In other words, F of 3 is 6. So this thing inside here is 6. So the whole thing I have is G of 6. And this is because F of 3 is 6. So I'm just plugging in like this thing. I know what this thing is. This thing is 6. So G of this thing is G of 6. And now I can look at the table for G. What is G of 6? 7. Good. All right. Excellent. Let's look at F of G of 4. And then I'll leave the last one to you. Oh, no, maybe we should do it together. Okay. Yeah, let's look at F of G of 4. So how do I get started with this one? We don't need this anymore. Excellent, Gabe. Yeah, first we just write down the definition. So remember that notation just stands for F of G of 4. And then we work from the inside out. So I look on the table for G of X. G of 4 is 6. So this is the same as F of 6. And what is F of 6? Good, it's 3, right? If we look back now on the table for F of X, when X is 6, F of X is 3. So F of 6 is 3. The last one here is a little bit more exciting. I want to find G of 6. This is fun, composing a function with itself. So to do this, I would get started the same way I did with the other ones. I just write down the definition. Okay, so that means this is G of 6, like so. And then I figure out what the inside thing is here, G of 6 itself, the innermost object. G of 6 is 7. Okay, so this is the same as G of 7. But now I run into something funny. Yeah, the table for G has no 7 as an input. It's very good. Yeah, we would say this is undefined. But 7 isn't in the domain of G. So G of 7 is undefined. Hence, semicolon, hence, G of 6 is undefined. All right. Nothing too bad, right? I think it's mostly about understanding the notation. Are there any questions on this problem? Okay. I want to then think a little bit about a little bit more about kind of machine diagrams and some stuff along those lines. In order to do that, though, let's talk. Well, actually, I've got a better notation for this. So we're going to start talking about one-to-one functions. Homework 15. Um, some functions send every input to the same output, like a constant function, for example. So let's begin with, say, recall. A function is a relation that sends each input to one output, right? That was at the very beginning of the semester, we talked about whether this thing is or is not a function, right? I would give you a graph or a table or something like that, and you would have to tell me whether the table did or did not represent a function. And the trick was to look and see if every input went to one output. In other words, no input could be sent to two different outputs. Another way to say this is, let's see, what's the nicest way to say this? Oh, we can just leave it like that. However, functions are allowed to send many inputs to the same output. Right? Think about, for example, the function f of x equals x squared. This is a function because every number has only one square, right? Like 1 squared is 1. 2 squared is 4. 3 squared is 9. 4 squared is 16. There is no input here that gets sent to two different outputs, right? There is no input which gets sent to two different outputs. That's what makes this a function, right? If there was any one input that got sent to two different outputs, then this wouldn't be a function. But because every number has one and only one square, right? You square a number, you get one particular number. It is a function. Every input does go to one and only one output. However, with the exception of 0, every output kind of gets hit by two different inputs. So sort of the notation for this would be 1 gets sent to 1. 2 gets sent to 4. 3 gets sent to 9, and so on. Right? Because 1 squared is 1. So the function f takes the input 1, inputs are over here. Now outputs are over here. And it's true that 1 gets sent only to 1, 2 gets sent only to 4, and 3 gets sent only to 9. There is no other number that is equal to 3 squared. There is no other number that is equal to 2 squared, and there is no other number that is equal to 1 squared. But these are not the only inputs that get sent to these outputs. Who else is associated with the output 1 in this function? What other number, when you square it, gives you 1? I know everybody in here knows this. Don't think too hard about it. Yeah, exactly. -1, right? -1 squared is 1. So -1 is also getting mapped to 1. -2 is also getting mapped to 4. And -3 is also getting mapped to 9. This is called a mapping diagram, and it's a way that mathematicians like to describe functions. There's a bunch of different ways to describe functions. Machine diagrams are useful sometimes. Mapping diagrams are useful sometimes. So we would say 1 gets mapped to 1, but also -1 gets mapped to 1. 2 gets mapped to 4, but also -2 gets mapped to 4. 3 gets mapped to 9, but also -3 gets mapped to 9. Does this break the definition of a function? Were we wrong? Is x squared not a function? I sure as shit hope f of x equals x squared is a function. We've been calling it a function all semester. This is fine, right? This does not mess up the definition of a function. If one input was getting forked to two different outputs, that would be bad. But here we have something else. We have two different inputs going to the same output. This is okay. but it does violate something else called being injective or one-to-one. In fact, if you look at this, every output gets hit by two inputs. We call this a 2-to-1 function. Does that make sense? For every output, there's two inputs getting sent to it. So two different numbers get sent to every one output. Two numbers get sent to this one output. Two numbers get sent to this one output. We call this a 2-to-1 function, or a 2-to-1 mapping. Today, I want to talk to you a little bit about one-to-one functions, why they're special, what we can do with them. But I want to make sure you're comfy with this idea of x squared being a 2-to-1 function. Are there questions about the notation or the language here? Okay. So mapping diagrams for functions. Well, let me give the definition. So a function is called one-to-one or injective. In Europe, France, or grown-up math classes, we call these injective functions. Everybody else calls them one-to-one functions. Called one-to-one if every output gets hit by one and only one input. Right? So this is the idea of a one-to-one function. Some examples of functions which are one-to-one. F of x equals 2x. This is one-to-one. Because every output, you want to find the input associated with that, just divide by 2. Mark brings up an interesting question. Odd functions. Some odd functions are one-to-one, but not all of them. I'm just on the side here. I'm going to draw the graph of each of these. That way we can make a connection down the road. So everybody remembers what the graph of 2x looks like, right? That's a line with slope 2 passing through the origin. Another example of a function which is one-to-one x cubed. X cubed is one-to-one. We said x squared is not one-to-one because when you take square roots, you get that plus and minus. But x cubed is one-to-one. When you take cube roots, you don't get a plus and minus. Every number has a unique cube root. Unique real cube root. And the graph of x cubed, you remember from your section on polynomials, looks like this. And it's kind of flat in here. It doesn't bloop up at all, just flat. flat for a brief second there. We said that the squaring function is not one-to-one. And we all remember what x squared's graph looks like. Looks like this. What other examples can we throw in here? The cube root function, or even, yeah, how about this? One over x. You guys remember what the graph of 1 over x looks like? He had some asymptotes. He was a little bit complicated. But he is 1-to-1. All right. What do you notice about the functions here which are 1-to-1 compared to the functions which are not 1-to-1? Do you see anything kind of interesting about their shapes? It's true, as Mark already mentioned, I think all the examples I've given you here of 1-to-1 functions do happen to be odd functions, but it's not true that all odd functions are 1-to-1, and I'll give you a counterexample in a second. Get these graphs in your notes. I'll give you a second to draw, because in a minute, I'm going to give you a theorem, and it'll be a fun thing for us to play with. So just some examples. The kind of geometric thing I want you to realize is that there's a connection between the geometry of the graphs and being 1-to-1. Let's look at another function that's not 1-to-1. The absolute value of x, this is not a 1-to-1 function. Much like x squared, this is a 2-to-1 function everywhere except at 0. And let's think just for a second about why. If I look over here at -1 and over here at +1, those are both inputs, right? They're on the x-axis. So I'm considering the inputs 1 and -1. Both of these get sent to the same output. Both of these get sent to the output +1. f of -1 is the absolute value of -1 is 1, and f of +1 is the absolute value of +1, which is also 1. So these two different outputs these two different inputs, two different inputs get sent to the same output. And geometrically, what that means is that along the graph, you have this point here, which is at the same height as this point here. And if you look at any function which is not one-to-one, you'll notice the same sort of thing. So this means there are two different points on the graph with the same y value. And if you think about it carefully, any function that fails to be one-to-one would have this feature. If you have two different inputs going to the same output, that means you have two different points with different x values that have the same y value. This is called the horizontal line test. Give it its name, horizontal line test. If the graph of f of x gets hit more than once by any horizontal line, then f of x is not one-to-one. So look here. If I draw the horizontal line, y equals 1, that hits this graph in two different places. This is a nice quick way to check that this function is not one-to-one. We just look at its graph and we imagine drawing a horizontal line. Any horizontal line anywhere up here would hit this graph more than once. So automatically we know it's not one-to-one. So this theorem is a very useful tool, especially since you guys have graphing calculators. If I give you a function, you can throw it into your graphing calculator and use the horizontal line test to see if that function is or is not one-to-one. So let me look at one more example here. Here we're going to answer a question. Is the function f of x equals x cubed minus x a one-to-one function? I'd like to point out that this is an odd function. It's a polynomial where the only powers of x that show up are odd. In particular, there's no constant term, right? The constant term is 0. So this will provide a counterexample to the first sort of thought there that maybe all odd functions are one-to-one if it were not one-to-one. Let's look at its graph. So let's, our solution here, graph f of x using the calculator. So I'm going to get out my calculator. I'd like you all to do the same. I'm going to hit the on button, clear this out. I'm going to come over here to y equals, and I'm going to type this function in. I do that by typing x, and then this button here to get into the power, and then 3, that's x cubed. Hit the over arrow to get down out of the power. You don't have to do this on the 83. You have to use parentheses for the power instead. Minus x. So here I have y1, so my first function y1 equals x cubed minus x. I'm going to check to make sure my window settings are reasonable. Yeah, this is the standard viewing window, -10 to 10, scale 1, -10 to 10 with scale 1. So then I'll hit graph. Now it's a little bit hard to see. So let me zoom in a bit. Let me change this to like -5 or even, sure, -5 to 5. -5 to 5, just zooming in a little bit. And I'll hit graph again. It's not looking good. Let me zoom in a little more on the y-axis. Change my y min to like -2, my y max to +2. Look at that. So I'll draw this graph real quick. And now we can use our horizontal line test to check whether or not this is one-to-one. For the purposes of determining whether this is one-to-one, I don't need any more detail than that on the graph. I ask, are there any horizontal lines that hit this graph more than once? So if I draw a horizontal line way up here, it'll only hit the graph once. That's okay. If I draw a horizontal line a little bit further down, that still just hits the graph more than once right here. But if I come down a little further, if I draw a horizontal line right here, that'll hit the graph 3 times. One, 2, 3. So since this horizontal line hits the graph more than once, this function is not one-to-one. What does this mean? It means, well, if I look at the output, whatever this y value is, there's actually 3 inputs that get sent to that output. Maybe this line is y equals 1/3. Let's say y equals 1/3 might not be big enough. Let's say y equals 1/10. Oh, or 1/5. Let's see what we get. Yeah, here we go. All right, so maybe this line is y equals 1/5. Then there's actually 3 places where this function is equal to 1/5. In other words, there's 3 inputs that this function sends to the output 1/5. Does that make sense? Are there any questions about how we came up with the conclusion that this function is not one-to-one? And I'd like to note again, and I'm not ripping on you, Mark, this is an odd function. This graph does have origin symmetry. It is an odd function, but it still isn't one-to-one. So some odd functions are one-to-one, but certainly not all of them. Is it possible for an even function to be one-to-one? So the observation that not all odd functions are one-to-one is an interesting one, and it's a very reasonable thing to think at first, because a lot of our basic examples are. But I'll reiterate the question. Is it possible for an even function to be one-to-one? Well, the graphs of even functions all have y-axis symmetry, right? Like this guy up here. If you have y-axis symmetry on your graph, then it's impossible to be one-to-one, because for every point like this, there's a corresponding point like this. So a neat note. Ready for a new page, yeah. Some, but not all, odd functions one-to-one. However, no even functions one-to-one. It's a cool thing. And if you go back and look at the graphs that we drew a minute ago as our first few examples there, you can use the horizontal line test on all of these. Right? This guy is one-to-one because no matter where you place a horizontal line, it'll hit this graph at most once. Same here, no matter where you place a horizontal line, it'll hit this graph at most once. This guy is not one-to-one because there's lots of horizontal lines that hit it multiple times. Even 1/x down here, as weird as he looks, if you drop any horizontal line, it will hit this graph at most once. That's a good question. There is an algebraic definition of being one-to-one. So if for whatever reason it's impossible to get the graph, another way to test and see if a function is one-to-one is to see if it satisfies the algebra definition. When we say that every output has a unique input from which it came, what that means is if x is not equal to y, then f of x is not equal to f of y. Or if you don't like using x's and y's, you can use an a and a b. I don't want anybody to get confused using the notation. In other words, if f of y is equal to f of x, then y had better be equal to x. This is one way to check algebraically. But it tends to be a little bit tricky. So we can use this to test whether a function is one-to-one, but your algebra skills need to really be on point. Usually this is given as the definition, and then from here we get the horizontal line test. So Kendra, your question is actually the same as Mark's previous question. No, origin symmetry does not guarantee one-to-oneness. So origin symmetry means that you are an odd function, but not all odd functions are one-to-one, right? This is an odd function, but it's not one-to-one. If you want to check algebraically whether a function is or is not one-to-one, you assume f of y is equal to f of x, and you must deduce that y is equal to x. This can be a little bit tricky. I can show you an example or two. Use algebra to prove that f of x equals 3x minus 7 is one-to-one. So what we would do is we would need to work with this statement right here. I don't think this is something that you guys are going to be required to do on the final. I don't think that this shows up in your homework as an algebra procedure. It might, but I don't think so off the top of my head. But it's worthwhile example. So the way you check something like this is you assume the first piece is true. You assume that f of y is equal to f of x, and then you need to deduce that y is equal to x. Or if you wanted, instead of using y's and x's, you could call it a and b. So we assume that f of y is equal to f of x, and we will try to deduce that y is equal to x from that. So what is f of y and what is f of x? Well, f of x is 3x minus 7. So what would f of y be? Yeah, very good. 3y minus 7. All right, now remember, my goal is to assume this and to arrive at this. So I just wanna fuck around with this equation and get rid of everything I can. I'll start by adding 7 to both sides. That gives me 3y equals 3x. And then I can divide both sides by 3. I get y is equal to x as desired. So yes, f of x equals 3x minus 7 is one-to-one. But in practice, the algebra steps here can get extremely complicated, right? It totally depends on the functions you're dealing with. Something like this, a linear function, is fairly easy to run through, but for a like degree 3 or 4 polynomial, this could be incredibly challenging. So generally, the graph is the easier way to do it, right? The horizontal line test is usually the easier way to do it. And especially since you guys have graphing calculators. We can always graph a function. Even if you don't know how to graph it by hand, you can always graph a function using your graphing calculator. So why are one-to-one functions important? This is all good. Now we know what one-to-one functions are. We know how to tell if a function is one-to-one. But why do we give a shit? Well, let me draw a diagram, a mapping diagram of a one-to-one function. So here are my inputs. Over here are my outputs. And I'm just going to pretend like I have a few things over here. I'll call them A, B, C, and D. And I'll assume that this is a one-to-one function. So, maybe over here I have like X, Y, Z, and W. And maybe the function f sends A over here to X. Maybe it sends B down here to W. It can send C over here to Z. If I want this to be a one-to-one function, where does D have to go? Don't think too hard. If I draw an arrow from D to W, would this be a one-to-one function? I apologize for the notation. So this is supposed to be a Y. But yeah, D has to come up here to Y. Since this function is one-to-one, there's an arrow going from each input over to one and only one output, and no output gets hit by more than one arrow. This is a one-to-one function. And what that means is that if I wanted to, I could turn the arrows around and the result would still be a function. I could send this arrow back in the other direction. I could send this arrow back in the other direction. I could send this arrow back in the other direction. And I could send an arrow from Y back down to D. And notice that whether you're reading it from left to right as the function f, or from right to left, which we would read as the inverse of f, the result is a function. So in other words, because f, the purple arrows, is one-to-one, the inverse of f which we denote like this, mapping, is a function. This is the big deal. One-to-one functions are those whose inverse mapping, the thing where you reverse the arrows, is also a function. I want you to take a second to make sure this diagram is clear in your notes. All right. So we're playing around with some concepts here. Yeah, in this case, the inverse is also 1-to-1. But the big deal is that it's a function. So let me show you another example. First, quick a definition. The inverse of a relation is another relation which sends all the outputs of the original back to the inputs from which they came. In other words, you turn the arrows around. Now let's see what happens if you try to invert something that's not 1-to-1. So I'm going to draw another mapping diagram. Same sort of thing over here. I'll have A, B. Maybe I'll just do it with 3 guys here, C. And over here, maybe I just have X and Y, just 2 outputs. If the original function f sends A to X and sends both B and C to Y, this is not a 1-to-1 function, right? F here is not 1-to-1 because f of B is Y and f of C is Y. The inputs A and B both get sent to the same output Y. So what happens if I try to construct the inverse? So I just turn all the arrows around. All right, so the inverse would send X back to A, but it would send Y to both B and to C. So F inverse here, F inverse is not a function. I'm not even able to talk about whether it's a 1-to-1 function or not because it's not even a function. It's not a function at all because Y, because F inverse sends Y to both B and C. Remember, a function is not allowed to take an input to 2 different outputs. The outputs for the original are the inputs for the inverse, right? Because that's what the inverse does. So note, outputs for the original, or the original are inputs for the inverse. That's why I'm not labeling these as input output because I don't want to confuse you. So while the original function f here is a function, the inverse mapping is not a function because y is an input for the inverse. And the inverse mapping sends its input y to two different outputs, both B and C. So a fact, the only functions whose inverses are themselves functions are one-to-one functions. In other words, in order for a function to have an inverse that is a function itself, the original function must be one-to-one. There's a bunch of different ways to talk about this, and I would love to talk. I can talk for hours about this shit and give you so many different ways to think about it, but we're limited in time. So what the inverse relation does is it sends all the outputs back to the inputs from which they came. Think of it as trying to like undo a code, or trying to figure out where all of those outputs came from. I could give you all the outputs and ask you, okay, can you figure out where these came from? If the original thing sends 5 different inputs to 1 different output, you can't tell me where that output came from. It came from all 5 of those different things. We can't specify a good inverse image for an output that got hit by more than 1 input in the original mapping. Okay. One last metaphor. Inverse metaphor. Inverting a function is running its machine diagram backwards. So you just change the direction of the assembly line, and that gives you the inverse. Now there's, again, a bunch of different ways to talk about this, and I've been trying to give you things that use language, that describe inverses in regular English language, but we also need lots of practice with the algebra. Unfortunately, we are short on time for today. So what I would like you guys to do is get into the homework on one-to-one functions. You need to finish the operations with functions homework. That will be due on next Tuesday. But the inverse and one-to-one functions, along with the quiz, I will extend those a little bit so that we can talk more about them on Tuesday of next week, because the class is technically over here. So while you do officially have all the things that you need to complete the inverse function homework and the associated quiz, I want to spend more time working with actual algebra examples, specific examples from the homework set, before I make it come due for you guys. So next Tuesday, we're going to talk a little bit more about inverses. I'll show you how to find them using algebra. It's not that hard. And we'll talk a little bit about kind of technical definitions and things like that. But please make sure you finish the operations with functions homework. And please do as much as you can on the inverse functions homework. There's quite a lot there. The first, you'll see, I'll show you really quickly as we go here. The first handful of problems is just like, is this thing one-to-one or not? You can do all of those. Here we go. So let me give you a goal to shoot for. I'll give you a problem number I would like you to finish through. Are you fucking kidding me? I don't know. You go down. Of course you couldn't. Expecting it to really start piercing. All right, assignment manager. All right, so I would like you guys to finish all of homework 14 and homework 15 up through, it's all good. Up through problem 10. Yeah, all right. So you need to finish all of homework 14, and please finish up through number 10 on homework 15. And then we will talk next Tuesday about how to do the things that they're asking for in like problems 11, 12, 13, and so on, how to solve for the inverse of a function. That is it from me for today, guys. Any burning questions before I let you go? Alrighty, that then is the end of our class for today. I will go ahead and get your exam 2 reflection open on Canvas. You can clean that up as soon as possible. Get that knocked out. You can earn yourself 3% bonus points on exam 2. If you have not taken exam 2, or if you did not submit work for exam 2, remember we got shit we need to fix and we want to fix it fast. So please get on that. Otherwise, I hope you have a lovely weekend, and I'll see everybody back on Tuesday.